Okay, so this week we're going to get into cement and concrete. Cement is something that we use to fasten the rocks or stones together, and they've been using it since early civilization to build tombs, fortifications, and temples. So at that time they used clay as a binder, and also gypsum and lime mortar. Mortar is nothing but just a mix, okay? And later in Rome civilization they use pozzolana and slate lime. So you mix this and then that. So pozzolana is just a volcanic ash that they found from Mount Vesuvius. Okay, that's in Rome. And slate lime is just a lime and heated lime, and then you crumble that by adding water. And then you mix them together, and you can be able to bind the stones together. Okay, and we call that binding material a mixture of clay or gypsum, lime, or volcanic ash and lime cement. So later we define cement as a finely pulverized material, and this material consists compounds of lime and silica, alumina, and iron. So here this is what cement looks like. It's just a mixture, okay, and we put lime, silica, alumina, and iron, of course powders. Hydraulic cement is the Roman pozzolana and slate lime cement. So that's the very first hydraulic cement. So hydraulic means something of water. So when the cement is in water, it hardens. Okay. So this property is very useful to bind material. John Smeaton, this guy in 1756, he discovered the cement made from limestone and with clay hardens under water. So the hydraulic cement is we make them by burning the mixture of lime and clay. Okay. You can do it at your home too. You can buy the raw materials like lime, and you can also buy the clay and then mix them up, and you're gonna get cement. And put it in the water, and it's gonna harden. So Portland cement, also known as your Quickcrete, is it was invented by Joseph F. Din. He is a bricklayer from Leeds. So what he did is he mixed the compound of lime, silica, alumina, and iron all together. So some people think that Portland cement is a manufacturer's brand, but it isn't. This Portland is just a reference to the Isle of Portland, which is off the British coast. Now when you look at the color of Portland cement, it resembles the color of stone quarry on that Isle of Portland. In the United States, we have naturally occurring cement deposits, and these deposits were found in New York, Indiana, and Pennsylvania. And we used them in the construction series of canal in the 19th century. So there was a large demand for cement. So later on, this guy, Thomas Edison, 1870, he contributed to the development of Portland cement industry in the US. 98% of all cement was manufactured in the US is Portland cement. So today, Portland cement is manufactured worldwide by many companies. When you look at the composition of cement, you're going to see 85% of cement is composed of lime and silica. And the common ingredients in cement are limestone, shells, chalk or marl. And you're going to combine these with shale, clay, slate, or blast furnace slag, silica, sand, and iron ore. The majority of Portland cement, we sell them to construction industry because it is an essential ingredient in concrete and mortar. And they are the world's most widely used building materials. We use concrete and mortar all the time, the mortar mix. You can see here shells, and then this is your slag and chalk. Okay, types. So type 1, we use it for general purpose cement, and other types like 2, 3, 4, okay, so and so produced by adding different chemicals to the mix because we want to use them for special applications. Sometimes you'll see A with the type of cements. So type 1A, so A means that cement is air entrained. So air entraining is nothing but we're adding sodium lauryl sulfate because this guy being incorporated in the cement along with clinkers during the production process is going to give air bubbles, okay, when you make concrete with that cement. So that air bubble is very important because it's going to give space to the concrete when it expands in high heat. So that way you can protect the concrete from cracking. So you always have to make some space for the thorough expansion of concrete. And one way to do it is to add a sodium lauryl sulfate in the cement. Okay, concrete is we use cement, stone, and water to make concrete. Yeah. So here you can see the bubbles. We call that the air entrained concrete. This is just a table and it's showing you the types. So you can see the type 1 and 1A standard, 1, 2A modified, 3, 3A high early strength, 4 low heat, and 5 sulfate resistant. These are the characteristics and uses. You just read through that, okay? No need to remember everything. And just pay attention that the concrete and the cement, the concrete depends on the selection of the concrete depends on the cement types, okay? Because you have to make the concrete by mixing the cement with water, stones, and something else. Yeah. So for construction purposes, we definitely want to use the air entrained. Okay. When we take a look at the chemistry of cement, we're going to concentrate on hydration, not just adding water. Okay. In chemistry, water is H2O, so we're adding H2 and O into the cement. And so the chemical process is going to cause the cement to harden when you mix it with water, and we call the entire process hydration. So here we're going to use a cement. So that's a tricalcium silicate. Pay attention, this is not the periodic table symbol, okay? This is abbreviations that they use in construction industry. So I don't know why they don't use the correct symbols like CASI04. It's supposed to be, but they use a C and then 3S to make sure that's it is calcium, and this one is a silicate. So this is not the periodic table symbol. That's just the terms, common terms that they use. Okay, not the real chemical formula. And we're going to produce a calcium silicate hydrate here. So after hydration, you get hydrates, compounds. Yeah. So here is your cement, your silicate. You're gonna put it in water. Yeah. And hydrogen from the water is going to go into the cement, and you'll be making the hydrates, compounds, yeah, along with your hydroxide. So when you look at the appearance, it's kind of like a powdery here, and then you're going to get kind of like a stone here on this side because water definitely hardens the silicates or your cement. So that equation 1 and 2 previously shown in the last slide. So they're just the hydration reactions, okay? So the reaction between the cement and water, they create heat. Okay, heat is again the particles moving around, and when you sense it with your our system, human system, we feel hot, so we call it heat. And so that heat amount is actually proportional to the rate of reaction. So reaction is nothing but these, when you go down all the way to the atomic level, these particles are moving and swapping bonds, okay? Some particle go into something else and something else go into another thing. So kind of like rearranging these bonds, and that you see as a reaction, and you can feel the heat or hot. And that amount is again proportional to the rate of that reaction, how fast the reaction is going. So the more movement you have, the faster the reaction. So the heat causes the cement paste, okay, to begin curing or hardening. So this heat is important for the cement to become hardened. So the end product is, I already showed you, calcium silicate hydrate. You can think of it like water goes, the hydrogen from the water goes into the cement, and the cement becomes hardened. So when it becomes hardened, you can see a paste, okay, cement paste. And you have to really use your strength to mix it, okay. Okay, so the very first step, the reaction creates a rapid heat evolution. So I'll put a heat the first, okay, 15 minutes, and then you're going to set it for 1 to 3 hours. Then stage 2, it doesn't have any kind of activity, so we get into inactivity stage. And in stage 3, you're going to have a maximum rate of heat evolution, so going on right after this inactivity. Okay, it's not shown here in the box. So stage 3 is happening around here, and then when we get to stage 4, you're going to use about 2 to 3 hours to set or harden. Okay, and then in stage 5, you're going to let it go for 12 to 24 hours to get the cement go into a steady state. So anyway, this is the details of your chemical process in the hydration reaction. Okay, so when we manufacture cement, we try to be environmentally active because it's so important for us to reuse and recycle things, okay? In efficient cement plant, in order for us to do the environmentally active manufacturing, resource recovery, utilizing waste material, okay, we do that all the time. So we use the oil and the scrap tires, okay. So these are the waste material, but then we use it in the manufacturing process because it's going to help the plant to reduce the fossil fuel consumption about 27% past 20 years practicing this type of manufacturing. It also helps conserve the coal and the natural gas. So they're the fuel that we need to use in manufacturing process in great volumes to heat the kilns, okay, that produce the Portland cement. and energy we recycle. So during the cooling of clinkers before grinding, we capture the heat, and then we use that heat to preheat the materials before being placed in the kilns. So here you can see this is a very large rotary kilns, okay? And this is where we make the cement to heat it up. So in managing the solid waste generated from the manufacturing process of cement, the cement dust, okay, from kilns is recycled back into kilns rather than being disposed to the landfill. And that's what we do in environmentally active manufacturing, is you use everything that come out if you can be able to use them back in the manufacturing process, okay? So waste materials from other manufacturing processes are also used as raw materials in cement making. So even though you have waste materials, you don't have to throw them out. We have to think about if we can be able to use them in the manufacturing process. So like slag from steel making, that's not a waste. You can use it in manufacturing of cement. Your fly ash, you can use it. Also use foundry sand, you can use it, okay? Because they're all sources of silica, calcium, and iron. And we need silica, iron, okay? Some calcium to make cement. So everything these materials can come out, we reuse them and recycle them. So here you can see in this photograph the typical incline of this one incline of the rotary kiln. Very, very big and giant, yeah. Okay, this is the end of the part 1 for Unit 7.